Okay, so thank you. And so I will start this lecture on seismology in some other place than Earth. Of course, feel free to stop me. So we'll have part on the past, part on the future. You know, at some place I will show you what we have done for the moon, mainly. And in another place, I will show you what we plan to do in some near future. So I will first start with the history of seismology, because I think it is very important to start with that in order to understand what are the goals of planetary seismology. If maybe in 50 years, some of you will have the possibility to claim that you will do 3D tomography of Mars or the Moon, whatever you can have. But we are just not at this level today. And in fact, what we want to do in planetary seismology is to restart seismology on another planet. So, and I don't know if you recognize this, but this is a very important start for seismology, because this is the first seismogram which was detected on the Earth. So you see, not so far away, by the way, it's 125 years. So, and seismology started almost at the same time as quantum physics at the beginning of the 20th centuries. And then, you know, you add a few years later, theoretician people, you know, were able to understand P wave, S wave, Rayleigh wave. And this is a paper of 1897. We are lucky in planetary seismology is that at least this work is done. There is no more theoretical work to do to understand the signal. Then you had the discovery of the crust, 1910, and then the discovery of the core, the outer core. It was done in 1906. And finally, you know, the discovery of the inner core in 1936. So what we want to do in planetary seismology is just to restart this. So nothing more. And if people say that you can do really much more, I think this is just not possible today. And therefore, we will forget this, you know, and seismology with 1,000 or 10,000 stations. So what I will do in my talk is I will forget the Earth, and I will show you what we have done on the Moon with 4 or 5 seismometers. Then I will show you what we will do, we hope, on Mars with 1 seismometer. And I will finish by proposing your idea to do seismology without seismometers. So to go to Venus or maybe the Moon. And what I will not show you in this talk is a lot of other places in the solar system. So I will really concentrate on the Moon, Mars, and Venus. I will not discuss anything on Jupiter. Jupiter is a very interesting place, because this is likely the first planet other than Earth where we have normal mode data today. And these normal modes are very fresh, you know, they come from Earth observation, and these are the peak of the oscillation of the surface observed from Earth telescope. And what you see a lot of peaks. And what is very important is that the distance, the frequency distance between the peaks is the same. And this is a clear signature of the possibilities that these are likely normal modes. So I will not discuss on Jupiter. I will not discuss on small bodies. So this is a simulation of a seismic wave in Eros, you know, with fracture and things like that. Small body is very interesting for seismology, because this is one place where you can link seismology with morphology of the surface, because the gravity is so small that the acceleration of the seismic wave are shaking the surface, and they generate landslide. And this landslide erases the small crater of the small bodies. So if you really want to understand the surface, the cratering history of small bodies, you need to do seismology. And of course, I will not discuss the sun. So this is not synthetic. These are data. These are data from SOHO, where you see all the dispersion branches just from the data, obtained by the satellite. And I will not discuss Europa, IO, where also you can do maybe exciting seismology in some decade in this century. So I will start with lunar seismology. It is not so much known that lunar seismology is a very old story in space exploration. In fact, 3 seismometers were on the Ranger's spacecraft, launched in January, April, and October 1962. None of the seismometers was able to work. There is still one orbiting around the sun, this one, and the other crashed, with the spacecraft. And then seismology was on Apollo, on the Apollo mission. And here you have a training of the crew in the Mojave Desert. And this is a seismometer on the Earth during this training. And of course, it was not only in Mojave Desert, as you know, even if maybe some people, I don't think that some people in the audience, believe that it is the case. But these are data of the moon. And so these are data from the Lunar Reconnaissance Orbiter. You see the crater here, but you see this very funny crater with a very elongated shadow there. When you take a better picture of this, you get this picture. So you see something like that, and you see a spot here, 3 spots, one here, one there. And if you take a picture on the moon, in fact, the spot there is a flag. The spot here is a laser reflector, and the spot there is a seismometer. This was the first seismometer of Apollo 11 with solar panel. And this seismometer worked something like 1.5 lunar day, so 1.5 months for us. After Apollo 11, they use a much more powerful source of energy. It was plutonium. And on Apollo 12, on Apollo 13, but this one did not went to the moon. 14, 15, 16 seismometers were deployed to build a network like this. The seismometers were like that. This was a really beautiful seismometer. It was a broadband feedback seismometer with a digital output, which was just completed by the end of the 70s. And if you ask, people on the digital record in the mid-70s, this was almost not existing on the Earth. A lot in many places we had seismology was still working with analog record, but this was already a very, very good seismometer. I think this seismometer was almost as good as the STS-2 in the bandwidth of the instrument. It was very expensive, I guess. It was done in beryllium. There is no way to do beryllium anymore, in fact, because this is very dangerous for the people working on the instrument. But it was a very good seismometer. So what was found on the moon is a big surprise. What was found on the moon was that the moon is very active in terms of number of quakes every day. The quakes are very small, but if you count the number of quakes every day, you get a lot of quakes. And the network was operating 7 years, from 69 up to the end of 77, and 13,000 quakes or impact were detected during the operation of the network. So if you divide that by 7, you get a lot of quakes. So what was detected by the Apollo station first were impact. The first impact were the impact of the upper stage of the Saturn IV rocket, or the impact of the lunar ascent vehicle after that one delivering the astronaut to the orbiting system on the moon. So therefore, it was falling down on the moon, and it was generating impact. And on this object, NASA was able to put a beacon in order to get the position, the timing of the impact. So therefore, these were really controlled, active source with known location and with known timing for the source. So therefore, like you can do in Earth exploration. And this is a typical data recorded by the Apollo 12 lunar module impact. The first thing you see here is the time. So this is the time in minutes. And these are the amplitude in digital unit. Okay, first, the amplitude in digital unit, you know, 1 digital unit, this was a very narrow seismometer, narrow band seismometer when working in that mode, very sensitive. So this digital unit, 1 digital unit is half an angstrom. So half an angstrom, it is about the size, the radius of the atom of hydrogen. So which means when you will see 4 is here. So this is a quake, you know, with unit 4. It means the peak, the maximum amplitude is 2 angstrom. So, you know, it's a very small displacement. Okay, it's always a little bit strange to imagine, okay, how can we detect a displacement of the ground by 2 angstrom or 1 angstrom? Because we imagine that, you know, even the rugosity of the ground, because of the atomic feature, you know, is much larger than that. But you have to see that it is a statistic displacement, and you have to see that there is nothing on the moon. There is no atmosphere, there is no wind, there is no ocean, and the only thing moving the surface are quakes in some way. So therefore, this was the point. The second point is the very long duration of the signal. You see, the signal length is almost 1 hour, not really 1 hour, but 45 minutes. Okay, the seismic wave propagate in the upper part of the moon at maybe 1-2 kilometers per second, because this is a very high porosity. You just take 45 minutes in second, you know, you will take 2,000 seconds to give you some idea, and you multiply this by 2 or 3, and you get 6,000 kilometers. So which means that the wave, you know, were propagating a lot of time along very long distances, even when the source was very close. It means that there is a very high scattering of the wave. The wave is not only going like this, but it is bouncing in a lot of places before reaching the station. And it's turned out that if you want to study the envelope of the signal, you end up with the fact that the best equation to model the envelope is not the seismic wave equation, it is the diffusion equation. It is mainly diffusion of seismic energy. So you lose a lot of the coherency of the wave. So almost everything you have seen in Earth seismology, you know, is lost because of this scattering. But nevertheless, there is the first arrival, you know. First arrival is something surviving all the time because of the Fermat principle. The P wave is the first arrival of the compression wave, and by definition there is nothing before. You know, you may have a lot after because of the scattering, but it will remain the first arrival of the signal. The same for S wave. The first arrival of shear wave will arrive at some time, of course with a lot of scattering after, but there is a first arrival. Then impact were detected. So impact are detected on the moon just because there is no atmosphere. And to give you idea, there are about 4,000 impactors with a mass larger than 1 kilogram impacting the moon per year. And some of the impactors we have detected were tons, 10 tons impactor. Every time impacting the moon at 20 kilometers per second, almost 20 kilometers per second, 19 in average. And therefore, this releases a significant energy between 0.1, a tenth to 1 ton of TNT in terms of power. Then we add the shallow event. Shallow mean, located in this place of the moon. So at depths up to 100, 200, 300 kilometers. So they are not really shallow. They are not shallow in the crust, but they are shallow in the upper mantle. And these shallow events you see are big guys. Okay, big guys, this means nanometer amplitude. And then we add the deep moonquake. So the deep moonquake, most of the time, were very, very small, and it was very surprising. This deep moonquake occur at depths of 800 to 1,200 kilometers, and they have very, very small amplitude. As you see here, you see that this step, in fact, are just related to the change of 1/2 angstrom of the ground. So therefore, this is really very small signal.
What is the cause of these shallow quakes?
Okay. The cause for the deep moonquake is the tide, and I will come back on that in next slide. We believe that the cause for the shallow moonquake is the thermoelastic cooling of the moon. Therefore, the moon is cooling a little bit, and this cooling releases stress, and the stress are dissipated by quakes. 27 shallow moonquakes were detected over the 7 years of the mission. So therefore, there is a very small rate, of course, of activity related to that. So if the moon was alone, not close from the Earth, we have only the shallow moonquake and the impact. And the impact, they are related to everything falling on our head. We are very lucky on the Earth to have the atmosphere, but this is not the case on the moon. So here you have the typical distribution of the quake as a function of the amplitude of the quake. The unit here is velocity, and this is 10 minus 10 meter per second ground velocity. And here you have the number of units per year, and you have the meteorite impact. In fact, the trend of the impact is almost linear to the mass, and this is something you find in the population of meteorite. So therefore, this is no more than the population of meteorite, and we have done some work to use this data, for example, to get the flux of meteorite on the Earth or on the moon, and we find the typical flux. Here you have the shallow moonquake, and here you have the deep moonquake. What was very interesting in the deep moonquake, so most of the quake, yes?
What is the difference between A1 quake and R?
Okay, so A1, A2, A3, etc., these are the location of the nest. And then we will go to this on this slide. So what is very, very strange on the deep moonquake are the following properties. Okay, so here you have the distance between the Earth and the moon in Earth radius. It is changing a little bit like that, just because the orbit of the moon is not a pure circular orbit. There is some ellipticity. And you know that the moon, I will say the moon is facing us with a near side, okay? But because of this ellipticity, there is a small twist called libration, and therefore the stress of the Earth tide on the tide made by the Earth on the moon, the stress are changing every month, like this. And here you have the number of quakes in 2 weeks. And what you see this oscillation of the number of quake, of the activity of the quake, which is completely and very strongly related to the distance between Earth and the moon. So therefore, these quakes are really triggered by the tide generated by the Earth on the moon. Yes?
I have two questions. The first one is, where do these deep earthquakes located? The second one is, how is the noise level on the moon compared to on the Earth?
Okay. So all the deep moonquake nests are located on the far side. In fact, they are located on the far side just because the seismic network was on the far side. And therefore, we have no idea on any nest on the, on the near side. Okay. All the nests are on the near side. We don't know what we have on the far side.
Okay.
So therefore, I suspect that we have a lot of nests on the far side, but these were not detected by the Apollo network. So this is the first question. The second question was addressing noise. Your second question.
The noise level on the moon.
It is not detected.
Okay.
So which means that when there is no quakes, the seismometer is flat.
Oh, that's cool.
No, it's not cool. It's not cool because you imagine all the seismology which was done in the last 5 years or 10 years, I will say disappear.
Okay.
Not all, but okay. But this very new way to do seismology without quake, where you use noise. Imagine if there is no noise, there is no way to do it. We made estimation on where is the noise level. Okay, we think that there is a noise level generated by the continuous impact on the moon, and we suspect that this noise level is something like a factor 100 below the Apollo resolution. So if you go to 100 times better than Apollo, then you might start to see continuous wave associated to the continuous impact on the moon.
Why you don't have background due to the cosmic rays? Your seismograph is about half square meter.
Mm-hmm.
You will have thousands of tera-electronavolt events from the deposition of energy from cosmic rays.
Okay.
Especially you may have it amplified if it's going into your electronics and is reading to so-called offset modes, etc. How you know that you don't have nothing there? Or why you don't have nothing there?
So probably the easy way to understand is that we don't detect that because the seismometer were not sensitive enough. Or if you prefer, they were well shielded enough with respect to this noise. I don't know the detailed answer because this is technology of the 70s. But it's turned out that when there is no noise, when there is no vibration, when the ground is moving by less than half an angstrom, the seismometer detects nothing. This is a fact.
Yeah, but if you're heating, you must have differential displacement.
No, because they were thermally regulated. Okay, the seismometer were thermally regulated to less than a tenth of degrees.
External temperature. You have a localized source of energy coming inside of your system.
Yes, this is but this is a Brownian noise, etc. But the instrument noise was put below the resolution. So.
But there is a lot of spikiness in the data, and also some of it is more related to when the day comes, right? When the thermal shock of the day comes.
Okay, the spike is mainly a transmission error, and it is due to the transmission property. If you go to the spike, you will see that most of the time the spike are a power of 2 of the digital unit because 1 bit in the transmission of the data, was corrupted. So this is for the spike. Then, indeed, at sunset, sunrise, there is what we call the thermal moonquake. And these thermal moonquake are small quake, maybe 5 meters, 10 meters away from the seismometer, generated by the thermal cracks of the surface. But strictly speaking, these are quakes. So these are really short period wave propagating to the instrument. So, okay, now we go to the details. So I will show you two stuff. The first stuff, very important, is that today all the Apollo data are available. You don't need to go to this stuff like that, okay? Or this was the Apollo 17 facility, you know. And this was done by the Japanese because the Japanese wanted to send penetrator on the moon at the end of, at the beginning of 2000. They were not able to send the penetrator. The mission was canceled, but they made all the effort to put the data from this tape to exabyte, and now the data can be requested on IRIS. It is a XB network, and you also can have the raw data at JAXA. So you can work with the data like you work with any Earth data. But there is even some discoveries. And it appears that the most recent Apollo seismic data were found by a former student of IPGP, Taishi Kawamura, now he's postdoc, somewhere, you know, somewhere in Texas. And these were the data of the gravimeter of Apollo 17. So NASA decided for Apollo 17 not to put a seismometer, but a gravimeter. And this gravimeter was supposed to detect gravity wave. Okay, not gravity wave of the moon, but you know, the big gravity wave generated by the collapse of stars, black hole, etc., etc. And the idea was in the 70s, physicists had the idea of what they call the Weber resonator. You know, these are stuff reverberating like that. You know, when there is a gravity wave, it is changing the shape of the space-time, and therefore it is making vibration of object. And they say, okay, so we take the best object not so far from the Earth. This is the moon, and we put a gravimeter there to detect the oscillation of the moon when a gravity wave is going through. And it turned out that the gravimeter was not well designed. They made an error in the spring properties. And the data look like that, you know. And the data, in fact, looked like that, and nothing came out from this gravimeter. So, and then Taishi Kawamura went to the gravimeter and took the data, and by filtering the data, you know, he was able to find that when you do filtering of this data with narrowband filter, you retrieve the moonquake. So therefore, we discovered 10 years ago a new seismometer on the moon, which was lost since 1974. Okay, so with this we can start to do seismology, and the typical seismology you do. So you take the seismogram. You know, here you have the time. Here you have the epicentral distance in degrees, and you pick up the P wave, you pick up the S wave. You know, the red dot are the P wave arrival time, the green dot are the S wave arrival time, and then you start everything classical for seismology, doing models, etc. Now, you have to see the main problem. The main problem is that we have a network. Okay, the first thing is we can only work with P and S arrival time. So we have a network, 3, 4 stations. We need to find the location of the quake. So we have 4 parameters. For the impact, we need to find the location of the impact plus the time. So therefore, this is the number of events. We put a model where we have n parameters. Typically, you end up with this. The collection of arrival time is about 350, depending on the quality you want. And here I count only the travel time where you have more than 2 stations. And therefore, at the end, you end up with about 100 degrees of freedom to make the inversion of the structure. Because, of course, you need to know where are the quakes before doing that. The big problem is the error. So this is a typical record. And this is, where Yoshio Nakamura will put the S wave, This is where it will put the P waves, the P wave, the S wave. And this is the differences between the arrival time error for different groups. So you had a group at MIT, you had a group in Texas, a group in Paris, and Yoshio Nakamura did that 20 years after, having done the wave picking the first time. And this is a typical dispersion between two groups. And this is 100 seconds. So, and this gives you the typical problem. So the typical problem is that, Monday, I guess, we had this discussion on the ghost, the 1 minute ghost on the travel time. The 1 minute ghost is there. Okay. So therefore, there is a big error. And again, there is a big error. Why? Because the P wave is very small, and even the half angstrom resolution is not enough to get it. And because of the scattering, the S wave is not clear. And therefore, depending on that, so you end up with errors. So, which basically means that we were able with our seismic model to provide error. Okay, so maybe it is the difference with PREM, but the other point is that the error bar is very large. So, and therefore, you have two ways to make a model of the moon. Either you make a very simple model with layers, okay, and the layers will not be more than the mean velocity in one layer. And then you reduce the number of parameters, which means you increase, the number of data constraining that parameter, and you reduce the error. The other way is you put a lot of layers, and then all the error is propagating to all these parameters. So, and these are the two extreme cases. This is the inversion done with many layers by Amir Khan, and these are the inversion done with a few layers, either by the group of Nakamura, myself and Janine Gagné-Pimbenex, or Goins and coworker. And what you see is that we have, and the last point is that you have this gray box, there, here. And this gray box is a model done without any seismic data, just from mineralogy. You take some idea on the mineralogy of the moon. So you see that we were able to retrieve the fact that mineralogy is good, but we do not really improve so much, I will say, the mineralogy information. So we are not in the process today to discuss from the moon seismic data what type of mineralogy you must have. Sometimes you have this step in the error. For example, there is this very famous discontinuity at 500 kilometers from the Nakamura model, which was not detected by Goins. It was not detected by us, and it appeared to be just, I will say, a change of the layer. And for a lot of time, you can find paper in geochemistry claiming that this is the signature of the base of the magma ocean, of the moon. So in fact, it is just the signature of the fact that we move from one layer to a second layer in the inversion. Yes?
Now you go.
Do you have an idea of, going back to that previous figure, why there is such a big difference or bias with the many-layer model in the lower part of the moon?
Yes, because of this error, I think that it is so noisy that when you in the work of Khan, he inverted as much layer as the 100 parameter I showed you. Maybe he put 50 layers without any correlation between one and the other one. So therefore, you just have a noisy data set, and you inject the noise in the noisy a priori model. For me, it is no more than this. And it is interesting that, for example, then the new way to process, Yes?
This might be a naive question, but you said that all of the deep earthquakes were on the near side.
Yes.
How can we therefore, how good can we actually resolve structure below those quakes at sort of the very deep?
Okay, we will come to that later. This model you see stop here. In fact, the answer is there. The moon is 1,740 kilometers, so it is stopping at the depth of the deepest deep moonquake. Okay, now the new way to proceed, of course, is to put mineralogy. You have two examples, this one and this one. The idea is you put mineralogy a priori and you invert, the data set, and you directly go to the mineralogical model. This is better, but of course it depends on the mineralogy you choose. This is for one model from Garcia, and this is another model from RAN, where two different mineralogy are used. Okay. Nevertheless, what is funny is that something came really from this data set and from the raw processing. The first stuff which came was the crustal thickness. So in the 80s, if you go back to the paper of the 80s, almost everybody claims that the crust of the moon is 60 kilometers in average. And when we reprocess the data, the group in Denmark found 38 kilometer depth. We found 30 kilometer depth. And basically, the point was we found that the velocity in the upper layers were much lower than it was used by the work of the 80s. And one of the reasons is illustrated here. We have seen yesterday a receiver function. No, it was a Monday receiver function. So this is a receiver function analysis of the lunar data. What is the idea of receiver function? So receiver function, you detect the arrival of phase converted somewhere below you, and therefore the only thing you detect is a time. Most of the time, the first thing you detect is a time. And here, this is the main arrival of a S wave. And what was found is that before the S wave, we were able to detect on two stations a precursor of the S wave, which is likely a S wave converted into a P wave at the base of the crust. And because the P wave is larger than the S wave, it is arriving about 8 seconds before the S wave. Now, a travel time, is a ratio between the depth of the conversion and, in fact, the difference of slowness. The difference, it is the product of the depth by the difference of slowness, and therefore it is not. If you increase the depth by 2 and if you decrease the slowness by 2, you get the same travel time. So therefore, you see that this is not telling you the difference between a fast crust, a fast thick crust, and a slow thin crust. On the other hand, the amplitude, give you some idea about that difference because the conversion are related to the velocity. And it turns out that, for a 30-kilometer crust, so we have this receiver function synthetics. This is the data. And for a 60-kilometer crust, we can get that one. And the only thing, which might suggest that this one is better than this one is the fact that the amplitude looks better in this case than in that case. So
why you have the 3 peaks after peak 4
okay.
in data?
So these peaks are related to the reverberation in the upper layer just beneath the station. There is a 1 kilometer regolith structure where we have reverberation. And in fact, this is something you find also there, by the way, for the precursor. You had a question?
I guess it's either a question or a comment, but these look incredibly narrow band filtered. Is that because of a requirement of the data, or just because that's how Lev likes to do his receiver function?
It is because of the data. So the seismometer had two modes. The first mode was a flat mode, flat in displacement, and the second mode was peak mode. And when the Apollo seismic team discovered that the seismometer were so small, most of the time it was not possible to detect the quake with the flat mode, but it was possible to detect the quake with the peak mode. And therefore they decided to use the peak mode because it was able to detect quake more than the flat mode. So this is the main reason. So therefore it is narrow band because this was the most sensitive way to get the data. Yes?
This might be a silly question. So the data, the 3 peak is higher than the 4 peak, but then in both the receiver functions, the 4 is higher than the 3. Is there any difference to that?
Can you repeat the question?
So with the data, the central peaks, the 3 peak is higher, slightly higher than the 4, but in both the receiver functions, the 3 is lower than the 4. Is there any problem with that? I'm not super familiar with seismology.
I think that, of course, we might prefer to have... Okay, so I think this... I will just tell you that it means that the model is not perfect. And there is still a lot of work to do.
But, so the premise is... but is the premise that the amplitudes are something that you're of keen interest in, correct?
Okay, I don't... Okay, I think that...
I don't know.
The data
is known well. The uncertainties on that receiver function must be huge.
Yes, you have to see that this is really... Okay, so this is really... Okay, first, it did not work on... It worked only on 2 stations and not on all the stations. And it was really a selection of the events, and there is only 1 publication. So I will be very happy to see a second publication, by the way, to challenge this, but there is only 1 publication. So again, this is moon seismology, and moon seismology, you have to be to accept that the data are not this nice data you have on the Earth. Okay, nevertheless, what are interesting is also impact. So impact was very interesting to get information on the crust, just because we know the depth of the impact. It is by definition at the surface of the planet. And then you see the idea, okay, maybe some of you will consider it is crazy. The idea was the following, is because we know the depth of the impact, then we can use this known information to invert the thickness of the crust. So, and this was done, with a natural impact, artificial impact. So this is an artificial impact, Apollo 17 near the station. This is a natural impact very far away. And what was done here by Lognonné was to use this impact to get the crustal thickness and to compare it to gravimetry. And again, I will say it was found that we get a crustal thickness of the order of 35 kilometers. So during maybe 3-4 years, in the last, I would say 5 years, a lot of questions were in the community, 45 kilometers, 35 kilometers, 40 kilometers, whatever you have. And the very strange point was that Grail, which was launched, 3 years ago and crashed last year, was able to demonstrate that the upper layers, the upper surface of the moon has a very high porosity, and basically Grail was able to confirm this crustal thickness of the order of 30 kilometers beneath the Apollo landing site. So now today we have a rather good story for this crustal thickness. Definitively, it is not the 60 kilometer of the 70s, and it is really something closer from 30. This might have a huge impact, in terms of understanding of the magma ocean, because it is controlling completely the amount of light element of the magma ocean. Yes, so GRAIL was a mission with two satellites. The two satellites were measuring the distance relative, the distance between one and the other by your radio system, And so basically, when you have a mountain like this, the GRAIL satellites are moving like that. The mountain is attracting the first satellite more than the second one, so therefore there is an acceleration of the first one, and then the second one sees the acceleration, and by getting the distance, you can get information on the density, because the precision is so high that you get the density, the lateral variation of the density. You don't get the mean density, but you get the lateral variation of the density. Because
Satellite, you measure from satellite or from Earth?
No. You measure that from one satellite to the other one. Okay. So this was sub-micron precision between the two satellites. So, and another point found by GRAIL is that this low rigidity likely extends to the mantle, and this was also something we found in the seismic model. So this is, an example of the seismic velocity for P, for S. And what we found, we found that beneath the crust, we have a big variation, a larger variation of the S velocities than the P, and we interpret this as an extension of the fracture through the crust, possibly up to the upper mantle of the moon. Okay, so the other thing we made on the moon was seismic source. So, and especially impact. Impact are very interesting because first there is almost no record on the Earth of seismic wave generated by the direct impact of the impactor on the surface. We have a lot of record generated by the excitation of seismic wave by the blast of the impactor or the atmospheric explosion of the impactor, but not by the real impact on the ground. If you take Chelyabinsk, for example, you know that Chelyabinsk generated a lot of surface wave of the order of magnitude 3.7. But if you also remember what you have seen on the TV, you remember that on the TV you have seen a lake with a small hole, and because the Chelyabinsk stuff, went through and break the ice. So therefore, the final impact of the object on the Earth was almost nothing. But it was a huge impact in terms of shock wave, and most of the signal was generated by the shock wave. So this is a typical impact, and what we found is that we have a very low frequency cutoff. This is even lower than nuclear explosion, for example. And also we work a little bit on understanding the source. So therefore, impacts are not like quake. The moment of a quake is like that. An impactor is more like this because it is an impulsive source. And something which is interesting when you get impact is to have in mind the following. So you have the impactor generates ejecta, and therefore you transfer to the planet not only the impulse of the impactor, but also the opposite impulse of the ejecta. It is working like a rocket, if you prefer. And therefore, you push 2 times the planet. And this is something we were able to retrieve in the seismic data. So we were able to retrieve the fact that the seismic source is amplified by a factor of 2 because of the ejecta generated by the impact. Okay, and now I will finish the moon with the core. And first, before 2010, so 2010 is not so far, you know. Seismology was in a pre-Oldham state for the moon. So therefore, the moon core was discovered by magnetic people, you know. They found the fact that there is a very small signal associated to the ejection of the magnetic field by the conductive core. You know that when you have a very conductive body, it is ejecting the magnetic field. You know, this is superconductivity. So if the conductivity is not as much as a superconductivity body, the ejection is smaller. And this is the ejection of the core. So therefore, the idea is you put a satellite around the moon. You know, this magnetic field is the magnetic field of the Earth's magnetosphere, and you get this small signal, the line, a line, and you feed this signal by this small signal. So the unit is 1 nanotesla. This is half a nanotesla, and this is a quarter of nanotesla. Huh? And on the x-axis, it is the orbit. I guess it must be. Okay, this might be for me. Okay, I'm not sure, but I think it is half an orbit around the moon. I have to check, but it's okay. It's probably the orbital distance. Okay, I have to check, but it is related to the orbital distance. But what you also have to see is that there is some noise in this fit. Okay, the second point was the libration. It was found in 2001 that there is okay. So there is a delay in the libration, which is associated to some viscosity in the moon. And again, you know, the idea was to put this viscosity in the core. And finally, Seismology came with two papers in 13, one by René Weber and the second one by Rafael Garcia. And the idea was to stack the deep moonquake for this deep moonquake focus here on the station. And you have to see that this looks strange, but all the deep moonquake from one nest, you know, have the same waveform because it is the same fault acting at different time, generating the same type of quake, propagating on the same path. And therefore, when you stack this, you can get the quake. And what was found was the following point is that if you take the seismic wave, the direct seismic wave, these are the red one, you take the shape of the seismic wave, you make the deconvolution of the seismic wave on the complete signal, then you find a peak of energy associated to the reflected blue wave on the core, arriving for core radius of the order of 300 to 400 kilometers. So this is a 1 sigma error, this is a 2 sigma error, and what you see is that you get this reflection signal at 2 sigma for a core between 350 and 400 kilometers. So therefore, this, I guess, responds to one of the questions. Now we get something from below the deepest moonquake, but again, we don't get something on a single seismometer. We need to use all the seismometers in order to get that. So this is the model we have. So this is the first model from René Weber. There is a strong signal associated to the core. There is 2 weak signal, and in the paper of René, the proposal is to assign one of the deep signal to the inner core and the second one to a partial melt layer. And in the paper of Garcia, you know, this paper addressed only the reflection at the core and proposed a core of 380 kilometers. And this is where we are today in terms of deep structure. What might be interesting is to know what is inside the core. So we can have some idea from, again, the inversion of geophysical data with either magnetism or seismic data. So there is a lot of work done in this topic. These are 2 papers of Amir Khan, and this is a paper done by Janine Gagnepin-Benex, myself, where we propose some temperature. The best way is to not to choose any paper, but to superimpose all the papers together. And what we get at the end is we get something like that, a prediction of the temperature, I would say, somewhere between 1,000 and 1,500 degrees, which is definitively too low to have pure iron, which is probably marginally too hot to get ilmenite. And today the best candidate is to have iron with light element for the core. So this is a view of the moon. And a lot of students are here, so you have the time to think on the future. It is very important for you to know something. Every 10 years or 5 years, there is a decadal report of NASA, So therefore, if you want to have some probability to fly on a big mission in the next 25 years, it is better to check that this is already on the decadal on the decadal survey. And it turns out that these are the priorities, for Telluric planet. And, the Lunar Geophysical Network is the 3rd. So it is not good enough for being selected in 2 years, I think. But it might be selected, in 5 years for a flight between 25 and 30. So therefore, I think there is definitively some work to do if we want to have new data. What we can do with the new data is we have worked a lot, on. Okay, so yes. Okay, so I don't know if you see this movie, but you will see a BIMP here. BIMP, like that. And it's turned out that now we have the way from the Earth to detect the impact by optical system. And in fact, this light is just the light generated by the plasma of an impactor on the moon. So therefore, because of that, we have thousands of free seismic sources falling on the moon, which can be detected from the Earth. So if you put a seismometer there, you will have for free a seismic source. You know the time, you know the location, and you can do a lot with that. Okay, so now I will move to Mars. And before that, I will give some idea for the tutorial. And what I will propose to do with you is to compute the amplitude of the seismic wave at 15 seconds, where you will not see the diffraction of the moon. Okay, this is a proposal I hope we will be able to go through. Okay, so now we go to Mars. Okay, so this is a advertisement to NASA of what we will do. Okay, so we spend a lot of time with colleagues to propose a network mission. This is the number of proposals done from 1980, you see. The green one means that they were selected sometime and disappear. And sometime also we add data, like for Viking. And as you might know, NASA selected a new mission InSight. I will discuss that a little bit. But before I discuss the 2 previous missions with seismometer. The first one was Viking. So the Viking lander landed on Mars. This is a lander. This is Mars. The seismometer did not land on Mars. This is a seismometer, and this is Mars. Okay. So, and the reason is that this was an exobiology-driven mission, and no place was available for the seismometer on the feet of the mission, and therefore, either it was a seismometer on the deck or no seismometer at all. And Don Anderson decided that, okay, it's better to have a seismometer on the deck. So the result was that Viking was detecting very well the oscillation of the lander in the wind. And therefore the seismometer worked quite well as a wind sensor. So second story was Mars 96. So this was great because we were supposed to have 2 of these stations with a seismometer on site, 2 penetrators, so a network of 4 stations. This was the last mission built by the Soviet Union, and it was a disaster on both sides, by the way. The mission fell down in the Pacific. So I was working on that, and the only success I had was to wake up with this mission, Bill Clinton, in the middle of the night, because the mission, the spacecraft we had 200 grams of plutonium on board the spacecraft, and this was falling down on the Earth. So at the end, it fell down in the Pacific. So. Yes. So, therefore, we know nothing on Mars. Okay. There is a lot of paper on seismic model. You can put the core where you want. You can do what you want for the mineralogy. It's complete freedom. We have one data for the attenuation related to the Phobos secular the Phobos secular acceleration, which tells us that the mantle of Mars is somewhere between the Earth's upper mantle and the Earth's lower mantle, which is good news. And this is something which was found again by NEMO 2 years ago. So the InSight mission, so therefore we hope will change that. So it is supposed to be launched very soon. So this is to stress me. In 1 year, 7 months, and 21 days. It will be a very fast mission, so it will take 6 months to go to Mars. And it will deploy a complete geophysical set of instruments. So we will have a seismometer, we will have a heat flow experiment, we will have a gravimeter, we will have a magnetometer, we will have a wind pressure sensor, we will have a geodesy experiment, and of course we have the boom to deploy. So what we want to do with this mission is first to deploy a seismometer like that. So this is a deployment of the gravimeter on Apollo 17. So it's easy. You see, you need to pick up, to grapple the instrument with a grapple system. Okay, I can put the sound, by the way. It's not so easy. This is real time. Okay, so we get it? Yes. And then we have to take care of the cable. Okay. The cable is quite a problem because if you break it, you have no data. And then you deploy it a few meters away from the power system. Okay, here we are. And finally, you put that on the ground. Okay, this seems to be a little bit crazy, but there is a good news here is that the Apollo 17 this is a gravimeter, and when they put it on, it was not working because of this design problem of the spring, and therefore it went up. And therefore they asked the astronaut to open the instrument and to fix it. So this is not something we can do on InSight. And on InSight, so therefore what we plan to do is basically the same. So we will pick up the seismometer with a grapple, we will deploy it on the ground. Okay, this is not real-time movie. It will take 2 months to do this movie. I would say 2. Yes. Why? Because first we land. Okay, we take MNT of all the rocks, then we rebuild in the GPL garden the rocks. Then we have 1 week to decide where we put the seismometer. Then we have 1 week to train the boom to deploy it on the unit at GPL. Then we send the command to deploy the boom, etc., etc., etc. We will take 1 week to decide to release the seismometer on the ground, Okay, etc. So it's not a problem, for me. I will be at JPL in California during 3 months. So. And then, okay, we cover the seismometer with a shield like that. Okay, and because I love also heat flow measurement, and then we deploy also the heat flux experiment, which is located there. Okay, and it is done. So this will be in fall 2016. Okay, so this is a heat flow. And in fact, this is what we call the heat flux tractor. And inside the heat flux tractor, there is a heat flow probe going up to 5 meter depth. This is a cable, yes. Yes. This is a nightmare. Okay, so these are the experiments. So the seismometer will be delivered by a European team. Also the MOL, there is a magnetometer from UCLA. There is a pressure sensor also from GPL, wind sensor from Spain, and there is the geodesy experiment from GPL. So I will go rapidly on the detail. You have in the note, for the tutorial, you have a tutorial I gave at GPL with all these details. So this is a configuration on the ground, and these are the details of the payload, but I skip on that. So now I go to the more challenging aspect. The big problem is, okay, we cannot imagine to have magnitude 7, magnitude 8, even magnitude 6.5 quake on Mars. So this will be low magnitude quake. The planet is much larger than the moon, so therefore we need to have a very good installation. And the big problem is that we are on a planet where there is wind, there is dust devil, we have shadows, we have temperatures, we have a lot of stuff, And therefore, there is a very big effort. And what we would like to do is we would like to do that, so to put the seismometer in a seismic vault. So therefore, we need to bring on Mars a seismic vault. And this was part of the challenge. So I illustrate this by these 2 figures. You have here the typical noise on the Earth. So this is period, and this is frequency, just to exercise you to the fact that the period is the inverse of frequency. Okay, so therefore the right is the left and the left is the right, without any other idea in my expression. Okay, so therefore these are the noise we target to get for the long period, for the short period. And this is the noise compared on the moon, On the moon, you see the noise of the short period is more than the noise recorded by Apollo. The noise of the long period is more than the noise recorded by Apollo. But on the Earth, you see that the noise is less. The noise we want to have on Mars is less than the noise recorded by a typical geoscope station. So therefore, this is one of the challenge. And we spend a lot of work on that, you see. So the idea is that we put the seismometer in a DWAR. The DWAR is protected by a thermal shield. The thermal shield is protected by a windshield. The windshield has a skirt here with chainmail. This is the first mission sending chainmail on Mars, such that the chainmail covers the rocks and there is no wind going through the skirt to disturb the seismometer, etc., etc. There is a lot of work done on that. And because of that, we think that we will be able to detect a lot of signal. I guess I have how much? 10 minutes? No? When we restarted? 15 minutes. Okay. So the first thing we will detect will be the atmosphere. I think the first data you will get, okay, the data will be available to the community 90 days after the beginning of the science monitoring phase. So the first data will be available to the international community by spring 2017. And every 3 months, you will have access to validated data. And we hope that starting May, June, we will be able to broadcast the data with a few weeks of delay, but this will not be validated. So the first thing you will see on this data will be atmospheric loading and atmospheric signal. And this is illustrating what we think we will see. So this is a pressure, in color. This is 780 Pascal, and this is 790 Pascal, And this is a pressure during the day related to the convection of the boundary layer on Mars. And you see that this pressure is, playing like that on the ground. And this will generate wave, deformation of the ground, etc. So therefore, we'll see likely trapped wave in the regolith. We will see ground deformation, etc., etc. And this will be the first thing we believe that we will see the planet breathing with the seismic noise. So this is a figure where you have the seismic noise, and this is the acceleration. And this is during 1 day. So therefore, you see you have this breeze of the planet associated to the daily activity and the night activity. So, but this is not really seismology, even if a lot of that stuff will be related to seismic wave. And this is also why we have pressure, wind, in order to understand this. Now, I go to in my last 10 minutes, I go to the signal. Okay, of course, we think that we will have other stuff than meteorology. And the first will be impact. So this is really something for sure, because we have a lot of data of impact. We know the rate of impact. We know the amount, the mass, the typical mass of the impact. We know the velocity of the typical mass of the impact. And so therefore, we can model that. And this is one example of impact. This is a picture taken on June 28. And this is a picture taken 1 month after. And this is just the impact on the Mars surface. So therefore, we have, again, the idea that the impact will be known source. We have 2 orbiters around the planet, so we can detect an impact on the seismometer. We request the orbiter to send us the picture of the surface, and you see exactly where the impact was. It gives you the position, and with that, you can do a lot of science. The impact will be sometimes very large. So this is, again, another impact, comparable to the Saturn IV impact, about 5 tons at 10 kilometers per second. And with that, you can do modeling of the number of impacts. These are the detection we expect, and all the dots are impact we expect to detect in this simulation. The difference between the black and the circle is the effect of the atmosphere. You see that the atmosphere of Mars is so tiny that it will not affect the big impact. It may affect the small impact. We will not detect, but not the big one. Now, we go to the quake. Okay, we hope to have quake. But we don't know. Honestly, we don't know. So this is a typical estimation of the activity based on the thermoelastic cooling. The same exercise as on the moon, And you can do a lot of work, Every time you end up with the same conclusion, the moon is Mars is between the moon and the Earth. So therefore, if you estimate the activity outside the plate tectonics, you end up with this number of quakes. But honestly, we have order of magnitude of uncertainties. It can be 1 order more, it can be 1 order less, and we don't know. But nevertheless, for the large quake, we can get maybe normal modes. So if we have a quake of magnitude 6, we will be able to get the normal mode with a not so good signal-to-noise ratio compared to the Earth, but with something reasonable. And this will be the second exercise for the tutorial. last but not least, for the quake not exciting normal modes, we believe we will be able to detect the R3 wave, so the wave having done one turn of the planet after arriving the first time. The wave arrived the first time. This is the surface wave, R1. Then it is making a second turn. And I don't know why, because maybe you want to stop here, but nobody asked me, okay, you have one station, okay, how can you get the seismic velocities? So, and the key idea is we can do seismology when we know the distance. For the impact, it is easy. You have the print of the impactor on the surface, so you know the distance. And if you get the R3 wave, the R3 wave has done a full turn of the planet. And we know the circumference of the planet, 2p times r. So therefore, we compute the time of R1. We get the time of R3. It gives us the travel time for one full turn. And when you have that, you can start doing seismology, modeling, etc. And finally, we also plan to do tide and maybe to see the core. And I will finish just for my last 5 minutes with the real future. So if some of you want really to prepare the new decadal survey for 2035. And the real challenge is Venus. It will be logical because this will be known and nothing will be there. So, and the idea, one idea for Venus is maybe to use the fact that Venus has a big atmosphere and there is continuity of the wave, So I am sorry I will say something bad, but everything you have learned in the first 2 tutorials is wrong. The surface of the Earth is not a free surface because there is a pressure of 1 bar. So therefore, the pressure is not 0. There is 1 bar pressure. And because of that, the wave, they hate to be oppressed. So they take their freedom and they go up. And therefore, the wave will go up in any planet with atmosphere, for sure. Okay. Mathematics is very easy. You have a wave, it's bouncing to the surface. There is an energy conversion related to the rate of acoustic impedance. So this is 1. This is 2 or 3,000. This is a few kilometers. This is a few hundred meters. So therefore, this is small. But it's bouncing, bouncing, bouncing every time you put energy in the atmosphere. And therefore, at the end, you can compute the energy with this very simple approach. And it gives you this. So this is the ratio of energy of a surface wave put in the atmosphere. So for Mars, you have 10 minus 3 of the energy in the atmosphere. For Venus, you have up to almost 10 minus 1. And for Mars, this is the Earth, 10 minus 3. And Mars, of course, is not good because there is a very little atmosphere. But the Earth and Venus are very good because you can see, you can get the wave in the atmosphere. So if you go at high altitude, then what do you have? You have the wave, and the wave is acting like a wind, and the wind pushes everything. It is pushing the particles, it is not a smoking place, but if it was a smoking place, I will ask someone, to smoke for me, and I will do that, and you will see the smoke going away, And in fact, the seismic wave is the same. The seismic wave arrives, and the seismic wave see electrons, see ions. Therefore, it is pushing the ions and the electrons through a collision process. And then these ions, they react with a magnetic field. And at the end, you transfer part of the seismic wave into ionospheric wind. Okay, so maybe you say, okay, why is saying that? Because you want to hit. So, no. It's turned out that we can detect that. I will show you one example here. So this is what we call a Doppler sounding. So we send a beam to the ionosphere. The beam is reflected by the ionosphere going down. And therefore, we can detect the velocity of the ionospheric layer. And this is a record of Doppler sounder data. It is recorded at 186 kilometers of altitude. This is a P wave. This is a S wave. These are the Rayleigh wave. So therefore, you see everything in the atmosphere. So now you can use GPS. And GPS will tell you the amount of electron, And these are examples of quake in Japan because there is a lot of GPS sensor. Magnitude 8, magnitude 7.4, magnitude 9, magnitude 8.3. And this is what you get. So you see the wave, propagating because these waves, they just are in the ionosphere, and you see the wave like that. And these are very big waves. You can get the Rayleigh wave, the body wave. Again, you can get everything. So now, because you really want to hit, I will finish with that. So now imagine that these waves, they go at high altitude, and then they start to react with the oxygen plus, and they react with the electron like this. And it turns out that normally, this oxygen and this electron, they react together to generate an excited state of oxygen, and this excited state of oxygen go to the fundamental state by generating a light, and this is a red light. And in fact, when you take a picture of the Earth, you see the red light here at 250 kilometers associated to the recombination of the oxygen with electron. This is not a big light, This is something like 10 milliwatt per kilometer square. But you see the light here, okay? And therefore, it's very easy, if the wave arrive here, shake the electrons, the oxygen, it will, at the end, modulate the light emission. So therefore, there is nothing fancy. It must work. And you can go to the computation. You end up with a light of the order of 100 microwatt per kilometer square. It's not a big light. And you will see this light here. So this is the light generated by the tsunamis. The tsunamis, they have the same story. They launch a wave in the atmosphere. So this will be a movie where you have in color the electron perturbation detected by GPS. And this is a picture of the red light from the sky. We have a camera in Hawaii. We look to the sky, So these are clouds because the seismic wave is above the clouds, so we have the clouds sometime. And at 8:30, you will see a wave coming from the north and related to the tsunami of Haida Gwaii, which was a small tsunami. So the amplitude of the tsunami here was 2 centimeters. Okay, 8:30. Now the wave arrive. You will see it there, you see. So this is basically the tsunami generating red light in the sky and detected from the ground. So it means that you really can see the wave, when you have this capability to get this very small light, either from the ground or from a spacecraft. And it gives me the way to finish my talk with the conclusion and the future. I think that this is what we can imagine in the future. We will have new data in 2016. Maybe we will have a return to the moon in 2020, 2025, in the best case, maybe 2030. And we probably will have, maybe in 10 years, the way to see the wave on the Earth from space. And of course, maybe later, we can use that to go to Venus and to go to the interior structure with whatever you imagine. It can be either from a satellite, it can be maybe from a balloon. If we put pressure sensor, of course, there is still the possibility to put a seismometer on the ground if you can have it surviving to 450 degrees for years. But there is a lot of future in this activity. So I will stop here and thank you.
How is the wave driving the chemistry of the
Oh, it is really okay. Yes, you take these chemical reactions; they all have a constant of reaction, so therefore you end up with a relation like this. Okay, I put in K the neutral spaces, so you end up with an equation like that, and you modulate this. And that's it. It is just chemical reaction. It is a density. It is a local density. So you increase locally the number of electrons. It's a density. It's really the density. It depends on the altitude. If you go to low altitude, the air glow is more generated by temperature. But there it is the air glow at high altitude, and it is really the density, which in some way is pressure. But it is from a chemical point of view, it is the density. And it is, like in chemistry, if you change the density of this, your reaction will move to adjust itself to the change of the density. The point is that it is not a big light, you see. So therefore we need to have very thin interferometer filters. If we see the moon, we cannot do the measurement. There is a lot of detail, but these are technology detail. If I take a 1 meter telescope, I put it on Venus, I will be able to see the seismic wave. The only problem is to put a 1 meter telescope around Venus, but it's a detail.
So in Venus, you don't actually expect a lot of not high number density.
We know that there is enough air glow, and we know that there is enough oxygen to do that. I will say it's turned out that there is a lot of oxygen air glow on Venus. And of course, after you have to, but this is something known. I will say the air glow is really the air glow of the planet with oxygen, with atmosphere is a very common feature, and this is very well documented. After you have to choose the right one, and this is here. You have, for example, for the oxygen, you have the green one, here you have the red one, and you have the UV one. In fact, the UV, okay, you have the green, the red, and the UV. And therefore, you have to choose the right ones and to adjust a very good filter in order to get no noise. And then you can get that. On the Earth, today we can do that for tsunami. We still cannot do that for seismic wave. And the reason is very simple, is that it is a problem of integration time. The tsunami are long period signal, and we need 5 minutes of integration to make the picture I've shown you. If you want to detect surface wave, you would like to do that in 5 seconds. And you cannot do that with a small camera like that. So you need a bigger camera. Yes?
Can you comment on whether these perturbations will decay as they travel through that? I mean, is there any attenuation happening?
Yes.
And the second question is, when you showed the structure of the moon from the Weber et al. Paper, the partial molten layer, that seemed like a big deal. Was there any testing done on something like squeezing out that velocity?
Okay.
I mean, is that needed by data?
Yes. So the first question is on attenuation. There is a huge attenuation starting at 250 kilometers, even for long period wave. And this is why, for example, on the Earth, we don't get 1 second signal in the ionosphere, so much, except for example, for Tohoku. For Tohoku, because it is a magnitude 9, we get all the signal. But for a magnitude 8, we get only the long period wave. The second question is what is the impact of the ionospheric structure? There is a very strong diffusion of the signal along the magnetic field line. When you go on Venus, there is no magnetic field, so it's good. But it is depending on the ionosphere. But the key point there is that this wave propagates at kilometer per second speed. And there is no physical stuff propagating at kilometers per second speed in the ionosphere. So therefore, you can filter the ionosphere by a very simple filter, okay? And therefore, you don't see the ionosphere. You just see, what is moving with frequencies which are completely unusual for the ionosphere. And this is why it is working very well. You can really detect very small stuff. Mike, I guess you... No?
Okay, last question. Does this concept apply to gas planets as well? We focused on terrestrial, but what's stopping?
Okay. We look on that for Jupiter and for Zeus, but then the problem is that you have to compete with the people. So the point is you need to be, first the payload is selected, so too bad, but it can work. But the point is, again, because you want to cancel the atmosphere, you need to filter it. You need movie. So the key point is you need movie. Therefore, you need to see the planet during maybe 30 minutes, 40 minutes. So you must be far away. And 95% of the planetary people, they want to be close. So there is a competition aspect, for the orbit, because for example, on Venus, you would like to be on MEO orbit, medium orbit. So 20,000 kilometers away, and of course, this is not easy to do or to share with the community. So.
I've been at 2:00 for Philippe's tutorial on normal modes. And then we will have at 4:00, we will have two talks, one by Bill White and the other one by Adam Jaworski before the party.